This lecture is about this two-dimensional or three-dimension motion, and we are discussing the projectile motion. So let's first go through this projectile motion and recap our previous ideas. In projectile motion, there is a object which is thrown, and it has a horizontal velocity component, and it is thrown upward with certain angle. Then we have seen that its position, velocity, and acceleration are separate equations for horizontal and vertical components. The component of the acceleration A are given as acceleration along the x-axis. The horizontal component is 0. The vertical component is minus g. It is downward acceleration due to gravity, and there is no air resistance. Since acceleration x and y both are constant, we can use equation of motion. First part is where the velocity along the x-axis is constant, component along the x v naught x. And if we integrate this with respect to time, we get x is equal to x naught plus v naught x times t. This is after the integration of this equation. And assuming that the value of x is equal to x naught when time t is equal to 0. For the motion along the y direction, we have acceleration equal to minus g, and the equation of motion is vy, vertical velocity component is v naught y, the vertical velocity component along the y direction at time t is equal to 0, minus g into t. Minus g is the acceleration part, and t is time. Now, if we integrate this equation, we get y equal to y naught plus v naught y times t plus half gt square. The plus sign is changed with the minus because it is downward acceleration. So we can also assume that the origin is at t is equal to 0, x0 and y0 is 0, and we can simplify. Here we show the velocity components as the projectile is moving in this blue colored line. We can see first the velocity vector has two components, v naught y, v naught x, then v1y, v1x, both here it is x. Similarly, when it reaches at the top, the velocity component along the y direction becomes 0, and acceleration is still minus g, and it has only horizontal component. Now, when it moves downward, the velocity component changes its sign. It becomes negative, the vertical velocity component, and the x component starts also as such uniform value, and eventually it touches the ground. We can see that the vertical velocity change is by the equal amount during the equal intervals of time. Horizontal projectile is in constant velocity motion. Horizontal acceleration is 0. So x, it moves along the x direction in equal distances in equal time intervals. If we decompose the initial velocity component into two parts, the first on the x-axis, the horizontal part, v naught x is v naught times cos of alpha naught, and the vertical part is v naught times sine of alpha naught. Upon substitution, we can get the velocity along the y direction and the y values as a function of time as shown here. V naught sine of alpha naught comes as a result of this vertical component. The projectile speed or the magnitude of the velocity at any time is given by the under root of v x square plus vy square, and the distance is x square plus y square under root. So we can have the equation of trajectory by eliminating the time from these two, the y equation and the x equation. So we get the y equal to tangent of alpha naught times x minus g divided by 2 times v naught square cos square of alpha naught times x square, and these are constant values. G is constant, v naught is constant, alpha naught is constant, tangent of alpha naught is constant. Therefore, we can safely write it as y equal to bx minus c into x square, where b and c are constant. And this is the equation of a parabola. So the trajectory or the path traced by the object is a parabola. Now we would like to find out the horizontal range, the distance from the starting point till it again touches the ground. The horizontal range is r. It is the distance of the projectile that has traveled when it turns to the initial position. The x we know is v naught cos of the angle times t, and r we will say it becomes range. And the range y value becomes 0. So from this equation, both of these equations, we can reduce and find out the range. From this, we find the value of t and substitute it back. It is v naught square times 2 divided by g into sine of theta and cos of theta. And we know 2 sine theta cos theta is sine of 2 theta. Therefore, the trigonometric identity says so. Therefore, range is v naught square divided by g into sine of 2 theta. The horizontal range will become maximum when the sine theta is 1. Sine theta becomes 1 when 2 theta will be equal to pi by 2. So theta will be pi by 4, which is equal to 45 degrees. So when theta is 45 degrees, 2 theta is 90 degrees, the range becomes maximum. The height is another issue, which is the vertical distance when it reaches to the maximum position. Height can be computed from the velocity along the vertical direction and the y value. You know, at this height, the vertical velocity component becomes 0 and only the x horizontal component exists. Therefore, when we substitute vy equal to 0 in this equation, we have the height, the simplified equation, and the height at that will be equal to h, which is equal to v naught sine of theta times t minus half gt square. And if we solve the both for t, we get h height equal to v naught square divided by 2 g times sine square of theta. We can use the relationship for the range also, which is given here, and make it height and range proportional to each other, and tangent of theta is there. The time taken to complete the whole thing is called the time of flight. So for the range, the total time is t equal to v 2 times v naught divided by g into sine of theta. And we can figure it out from this relationship for the total value. So in this case, for a projectile motion in which a ball is thrown at a certain angle with some velocity v naught, Then the ball reaches at a maximum distance, horizontal distance of r. It goes to height of h. The total time taken is t, and we have already calculated all these for a given angle theta. Now we also know this, that the trajectory or the path traced by this object is parabola, and it obeys the equation ax minus bx square equal to y. Now let us talk about another important idea, which is a uniform circular motion. A uniform circular motion describes the motion of a body which is traveling in a circular path at a constant speed. Since body is describing a circular motion, its distance from the axis of rotation will remain constant, which is equal to the radius. Though the body's speed is constant, its velocity is not constant. Its velocity vector is changing all the time. And this quantity, the vector, velocity vector, depends on body speed and its direction. The acceleration is in turn produced by the centripetal force. The centripetal force, which is also constant in magnitude, and it is always directed towards the center, towards the axis of rotation, and it is shown in the figure here as F force, directed towards the center for all the positions. So anything which is moving in a circle, a uniform circular motion, will be obeying these things. For a uniform circular motion, this figure is showing that a particle is moving with a constant speed in a circular path of radius r with the center O. The particle is moving from P1 position to P2 position in delta t time. The vector is changing its the velocity during this time as shown below. The vector is v1, and then there is a vector v2, and there is a v delta v, so change in the velocity. So the ratio of the sides of the similar triangles are equal, and therefore delta v over v1 and delta s over r are same, and therefore we can say that the average acceleration during time delta t is delta v divided by delta t, which is equal to v1 divided by r multiplied by delta s over delta t. The s is the curved path. If time interval is short, then delta s distance move along its curved path. So the limit delta s over delta t is the speed at the point P1. So we can write the radial acceleration as v squared divided by r for a uniform circular motion. So remember, in a uniform circular motion, the magnitude of acceleration, the radial acceleration of the instantaneous acceleration is equal to the square of the speed divided by the radius r. So its direction is perpendicular to the velocity, and it is always inward towards the center along the radius. Because acceleration in a uniform circular motion is always directed towards the center, it is sometimes called centripetal acceleration. In many situations, it is very convenient to describe the motion of particle moving with a constant speed in a circular radius r, small r or capital R, in terms of the period t. The period is defined as the time required for one complete revolution. So the magnitude of the acceleration can be expressed in terms of this period, the time for one revolution, one complete trip around the circle. In time t, the particle is traveling distance equal to the circumference, which is 2 pi r. So the distance traveled divided by the period is velocity. Therefore, the acceleration is v square divided by r. Therefore, we have 4 pi square r square divided by r, which means it is only r divided by the period time square. In a circular motion, the acceleration vector can be resolved into two components. One is a radial component vector AR, and the other is tangential component AT. So acceleration can be written as a vector sum of these two vectors, the radial component plus the tangential component. Keep in view that a tangential acceleration is caused by the change in the speed of the particle. It is parallel to the velocity, and its magnitude is given by acceleration equal to dv divided by dt. The radial acceleration rises from the change in the direction, and the direction of the velocity vector described earlier has absolute magnitude. Acceleration is v squared divided by r. So remember that in uniform circular motion, radius r is the radius of curvature of the path at the point in question. For example, in this figure, A point and B point and C points are shown. We can see these points here, A point and B point and C point. Because A radial and A tangential are mutually perpendicular to each other, as we can see here, the tangential component and the radial component, the radial component and the tangential component, the tangential component and the radial component. So AR is a non-uniform circular motion, is always pointing towards the center of curvature. We can see here it is the radial component, it is always pointing towards the center, circle, center, circle. Uniform circular motion, we have the constant velocity, therefore A tangential is 0, and the acceleration is always completely radial part. The radial is always directed towards the center. So in uniform circular motion, it is very special case of a moving object along a curved path. The curved path can be, as we have shown here in the above figure. Let's do one example on circular motion. Here we have a ball which is tied to the end of the string, 0.5 meters in length, and it is swinging in vertical circle under the influence of gravity, as it is shown here in the figure. We see the radial part and the tangential part of the acceleration directed towards the center of the circle, and we see the gravitational force downward. When the string is making an angle of 20 degrees with the vertical, the ball has a speed of 1.5 meters per second. We are asked to find the magnitude of the radial component of the acceleration and what is the magnitude of the tangential component of acceleration when theta is equal to 20 degrees. Now, to solve the problem, radial acceleration is given by the equation v square divided by r. So v is 1.5 meters per second and the length r is 0.5 meter. So we have acceleration, which is radial acceleration directed towards the center. It is v square divided by r. And the answer is 4.5 meters per second square. The other part is when the ball is at angle theta to the vertical, it has a tangential acceleration which is equal to magnitude g into sine theta. So this component, the tangential is g sine theta, and theta is 20 degrees. Therefore, the tangential acceleration, which is shown here, is g times sine of 20 degrees equal to 3.4 meters per second. Another part is find the magnitude and the direction of the total acceleration. So the total acceleration at angle theta equal to 20 degrees is given by the radial part plus the tangential part vectors. Sum of these two vectors will give the total vector. So the magnitude of the total vector is equal to the radial part square plus the tangential part square under root. And we have the values AR equal to 4.5 and AT is equal to 3.4 meters per second square. When we substitute and solve this, we get the total acceleration 5.6 meters per second square. This is the magnitude of the total acceleration, and now comes the angle. So angle, let us say it is phi, which is making with the normal path. Then this is equal to the A total, A tangential divided by A radial. That is what the picture is showing us. So tangent inverse of this will give us the 37 degrees, and that's the circular motion of a ball which is hanging with the help of a rope from a center, and it is downward, vertically downward, and we have solved to figure out the both components of the acceleration and figure out what is the total magnitude and direction. Another important concept that we must have in physics is that the velocities and acceleration and how they are relative to observers in different frames of references. In general, when there are two observers and they are measuring the velocity of a moving body, then they can get different results. If one observer is moving relative to the other, then for sure the two persons will have the different results. Velocity seen by a particular observer is called velocity relative to that observer, or simply the relative velocity. So a particle which is located at position A, as shown here in the figure, now we can describe it by the two observers. They are in the fixed frame of reference S and S dash. Now, S dash is a frame which is moving with the velocity V naught. It is a constant velocity with which it is moving. Therefore, this person, the person in this frame will observe differently as compared to the person who is sitting here at the origin of S. The vector R is particle's position vector relative to S, as you can see here. Similarly, the vector R dash is a position vector relative to S dash for the same position, but the origin measured from the origin O dash. You know very well that O and O dash are moving, and their distance is changing between two origins, and this distance is V naught into T. So as the time progresses, the distance progresses. For relative motions in classical mechanics, we have the transformations. They are called Galilean transformations. And let's first label and then study. We label the position of the particle relative to S frame of reference, which is what we call stationary frame. Its position is R vector. And relative to S dash frame, which is moving frame, with the position vector R dash. Both are being measured at time t. After some time t, it is being measured. The vector R and R dash R can be seen from this triangle. The two vectors, the sum of these V naught t vector plus R dash vector will make the R vector. Therefore, R dash is equal to R minus V naught into t. This is called Galilean displacement transformation. That is, after some time t, the S frame is displayed to the right of the S frame. If we differentiate above equation with respect to time, we note that V naught is constant. Therefore, dr dash by dt is equal to dr by dt plus V naught times 1. This is velocity in the S dash frame. This is the velocity in S frame, and minus the V naught is the sign which is telling us that one frame is moving with velocity V naught with respect to the other. So V dash is the velocity of the particle observed in S dash, and V is the velocity observed in S frame, and the above equations, both equations, the velocity transforming equation and the object distance is part of the linear transformation equations. What do they do? The linear transformations relate coordinates and velocity of a particle as measured in frame, which is fixed relative to Earth, to those measured in a frame that are moving with a constant or uniform motion. So although the observer in two frames measure different velocities of the particle, they measure the same acceleration. That is what we are going to observe now. We can verify this by taking time derivative of the equation dr dash by dt is equal to dr by dt minus V naught. And V dash is the velocity, dr over dt as a V dash, and dr dash and dr over dt is simply V. Therefore, V dash is equal to V minus V naught. Again, velocity can take a derivative of the velocity, and dv dash divided by dt is actually dv over dt minus dv naught by dt. Remember that the v naught is a constant, therefore this derivative of a constant with respect to time is 0. Therefore, we conclude that a acceleration in the prime coordinate system is really equal to the acceleration in the unprimed that was a stationary. So a frame which is moving uniformly and a frame which is at state of rest, both have same acceleration. A prime is equal to A. So acceleration of particle measured by the observers in two different frame of references remain same. They can be measured from a stationary frame or from a constant moving frame. Both will show the same result. Let's do one example on this transformation. A boat is headed towards north, crosses a wide river with a speed of 10 kilometers per hour relative to water. The water in the river has a uniform speed of 5 kilometers per hour. It is due east. Now, question is, determine the velocity of boat with respect to, relative to, an observer standing on either bank. The solution is simple. First of all, let us write down the symbols. The velocity BR is velocity of the boat relative to river. Similarly, velocity RE is the velocity of river relative to earth. Then is velocity BE, it is the velocity of boat relative to earth. Now we are asked to find the velocity of boat relative to earth. Now we can see here the velocity of boat relative to river, VBR, and velocity of a river with respect to earth is this vector. Adding these two vectors, we get a resultant vector which is the velocity of boat relative to Earth. So we can write the velocity of boat relative to Earth equal to VBR plus VER as shown in the vector addition of these two important vectors. So we can find the speed BE equal to the boat's velocity relative to Earth by using Pythagoras theorem, which is VBR square plus VRE square, and the answer is 11.2 kilometers per hour. We can also tell what is the direction theta of this velocity of boat with respect to Earth. So this vector, this vector angle is tangent theta equal to VRE divided by VBR. The velocity component, velocity which is of river with respect to Earth, divided by velocity of boat with respect to river. So it is 5 divided by 10. And since it is 5 divided by 10, the answer of tangent inverse of this half is 26.6 degrees, and the magnitude already is 11.2 kilometers per hour. So we can say boat is moving with a speed of 11.2 kilometers per hour, and it is in the direction of 26.6 degrees of north relative to east of north relative to Earth. So it is going in this tilted direction. We will continue our discussion on motion in next lecture. So we conclude now the ideas of the curved path and motion in a curved path, and we have covered the idea of motion of a projectile, and we have seen also when objects are moving in straight line. The two different frames that are inertial frames, they also are related to each other, and the acceleration in one frame remains same as compared to the other frame. Both, although are moving relative to each other, but the acceleration is constant in all that cases. If acceleration is constant, then net force is constant, according to the Newton's second law. Thank you so much. We stop here.